This is a Turbocor chiller. It's packed with technology, from a variable frequency drive, a soft starter, dual impellers, an electronic expansion valve, and even magnetic bearings, which levitate the shaft of the compressor. So we're going to learn the basics of how this unit works in this video, which is sponsored by Danfoss, the leading manufacturer of oil-free compressors and the pioneer of the Danfoss Turbocor compressor, the award-winning oil-free magnetic bearing compressor for the HVAC industry. Learn more about Turbocor and take the Danfoss free 12-course training program for how to work with their oil-free technology using the link in the video description down below. Like any refrigeration system, we have the main parts being the compressor, the condenser, the expansion valve, and the evaporator. The evaporator is usually covered with insulation to help increase efficiency. The compressor will push refrigerant between these main components to remove the unwanted heat from the building. In this example, we also find a filter on a small diameter pipe entering the rear of the compressor. This is transporting refrigerant into a separate circuit to cool down the compressor and the electronics. The evaporator and condenser are shell and tube type heat exchangers. The refrigerant typically fills the shell and surrounds the tubes. Water is then pumped through the tubes to either heat the refrigerant or cool it down, which will cause it to change between a liquid and a gas. We'll see how that works a little later in this video. Valves are usually found on the evaporator and condenser to allow these parts to be manually isolated if needed, for example, during the replacement of a compressor. The compressor is the heart of the system and pushes the refrigerant around the inside of the chiller. It sucks in low pressure, low temperature, slightly superheated vapor refrigerant from the evaporator via the suction line. The compressor squeezes this into a smaller volume, so the refrigerant leaves via the discharge line as a high pressure, high temperature, superheated vapor. Instead of a piston compression chamber, the Turbocor chiller actually uses an impeller and volute to manipulate the refrigerant's velocity, kinetic energy, and static pressure. We'll see that later on in this video. The refrigerant is a specially designed fluid which can easily change between a liquid and a gas because it has a very low boiling point. Inside the compressor, we find the power electronics. We have the three-phase AC input terminals. Then we find the silicon-controlled rectifiers, which is converting the high-voltage AC into high-voltage DC. This will then travel along the DC bus bars. We also find a soft starter. This reduces the inrush current when the compressor first turns on. It sends a signal to the rectifier, telling it to slowly allow more current to flow into the DC bus bars. Connected to the bus bars are some large capacitors, which are mounted to the side of the compressor. These will smooth out the rippled DC waveform produced by the rectifiers to ensure clean DC electricity is supplied to the inverter. We also have some small snubber capacitors, which remove the noise and harmonics from the waveform before the high voltage DC enters the inverter. The inverter is located underneath the soft starter. It consists of some IGBTs, which convert the clean high voltage DC into a variable frequency three-phase supply. This is sent to the electrical motor inside the compressor to control the rotational speed of the impellers. We'll see that in just a moment. Alongside the inverter, we find the high voltage DC to DC converter. This is used to change the DC voltage level and supply the different electrical control circuits of the chiller. It receives the high voltage DC and converts this into a much lower voltage. We have 24 volts DC for the control circuit board and around 250 volts DC for the magnetic bearings signal amplifier. On this side of the unit, we find the control electronics. There's the backplane, which physically connects all the different control modules and sensors, the serial driver module, which controls the various stepper motors, solenoid valves, and expansion valves, and it contains relays for compressor run status, etc. Next, we find the bearing motor compressor controller module. This uses the feedback data from various sensors to control the electromagnetic bearing and shaft position. It also controls the motor speed, as well as ensuring the compressor is operating within its design limits. The final module is the bearing pulse width modulation amplifier. This uses high voltage switches which turn on and off extremely fast at high frequency to control the current to the electromagnetic bearings inside the chiller. These are controlled by the bearing motor compressor controller module. Then, as we look inside the compressor at the mechanical parts, we see the inlet guide vanes at the front on the suction inlet. These blades can vary their position and cause a refrigerant to swirl as it enters the compressor impeller. These are driven by an internal stepper motor. The serial driver module controls this motor, and the bearing motor compressor controller determines when and how much to rotate them. These are used during low cooling loads to improve the efficiency and avoid chiller surge, but in normal operation they are usually left open. Then we have the two-stage impellers. These rotate together. The refrigerant passes through the first impeller and then through a small channel and into the second impeller before entering the volute. From here, it will be ejected from the compressor. The refrigerant pressure increases each time it passes through an impeller. The impellers are attached to the shaft, which runs the length of the compressor. The shaft passes through the electrical motor stator. The shaft contains permanent magnets in the rotor section. These will interact with the electromagnetic field produced by the stator coils of the motor. And because magnets attract and repel each other, we use this to force the rotor to rotate. The variable frequency drive controls the speed of rotation. The bearing motor compressor controller determines the required speed. The shaft is held in place by 3 bearings. The first 2 are radial bearings, and the rear is an axial bearing. These 3 bearings are magnetic and have no moving parts, so there is no friction, and thus they do not require oil. They create strong electromagnetic fields which levitate the shaft. Proximity sensors monitor the position of the shaft, and the pulse width modulation module sends signals to alter the magnetic field and keep the shaft aligned and central. The heat generated by the compressor is removed by diverting some refrigerant through an internal channel around the motor and also underneath the power electronics. This is a water-cooled chiller, meaning the condenser is cooled by pumping water through it. We can also get air-cooled Turbocor chillers, where the heat is removed by moving ambient outdoor air over the condenser. Around the building, we have a number of air handling units and also fan coil units. These contain fans and heat exchangers. The fans distribute and recirculate air within the room or the zone. This is forced through the heat exchangers. We pump chilled water through the heat exchangers, and this will absorb the unwanted heat from the air. So warm air from the room enters. The heat is removed, and the air re-enters the room much cooler. The water enters cold. It collects the heat and then leaves warmer. This relatively warm water returns to the chiller and enters the evaporator. The evaporator is typically a shell and tube type heat exchanger, with the water flowing through the tubes and the refrigerant surrounding the outside of the tubes. The refrigerant has a very low boiling point, so the temperature of the water is enough to cause the refrigerant to boil and evaporate. The refrigerant is absorbing the thermal energy from the water. This energy passes through the tube wall. The refrigerant and the water never meet or mix. The water therefore enters warm and leaves cooler. This chilled water is then sent around the building to pick up more unwanted heat. The vapor refrigerant, which is evaporating, is sucked into the compressor. The compressor's impeller increases the velocity. The diffuser then slows this down. The kinetic energy is converted to pressure and the temperature increases. This is then sent to the condenser and released into the shell. Another stream of water is flowing through the condenser, known as the condenser water. As this water flows through it, it absorbs the thermal energy of the refrigerant. This removal of thermal energy causes the refrigerant to condense into a liquid and accumulates at the bottom of the condenser. The condenser water therefore enters cool and exits warm. This is then sent to the cooling tower, which is usually located on the roof. The cooling tower uses a large fan to force ambient outdoor air through it. The condenser water is typically then sprayed into this airstream. The air will absorb the thermal energy of the water and carry this away into the atmosphere. This means the condenser water enters warm and exits cooler, then heads back to the condenser to collect more thermal energy. The ambient air enters cool and exits warm. In this type of chiller, the expansion valve is typically used to control the liquid level in the condenser or sometimes the evaporator by monitoring the liquid level sensors. Alternatively, it could control the level of superheat on the compressor suction line, although this isn't recommended for this type of chiller. It will try to maintain a certain level of superheat, which basically means the refrigerant has been heated past its boiling point so that no liquid can exist. That's important because compressors can only compress gas. Liquids cannot be compressed. The Turbocor compressor can pass a small amount of liquid with the gas, but if too much liquid enters, the compressor will stop. To maintain the required level of superheat, the expansion valve opens and closes small amounts to increase or decrease the amount of refrigerant entering the evaporator. It uses an internal stepper motor to achieve very precise control. By the way, we have covered how electronic expansion valves work in detail in our previous video. Do check that out, links can be found in the video description down below. The unwanted heat of the room has therefore been collected by the chilled water and transported to the evaporator. The refrigerant absorbed this and the compressor transferred this to the condenser. The condenser water absorbed the thermal energy and transported this to the cooling tower, where it was removed from the system and released to the atmosphere. Turbocor compressors are currently the most advanced type of compressor available. They are also the most efficient. This is because it has so much technology built into it. First of all, we find a two-stage compressor. The evaporator is low pressure. The condenser is high pressure. The compressor increases the pressure, and instead of a single large impeller, we use two smaller impellers which work together, increasing the pressure in stages. Stage 1 increases the pressure to roughly half the difference. Stage 2 increases the pressure the remaining amount. Refrigerant is pulled in through the guide vanes and into the impeller of the first stage. This will exert a centrifugal force onto the refrigerant particles, forcing them to increase in velocity and move towards the outer edge of the impeller. This then passes through a diffuser, which slows the high velocity refrigerant down. As it slows down, the velocity is converted into pressure, and this is then pulled into the second stage. This second impeller sucks in the high pressure refrigerant. It again increases the velocity. The refrigerant exits the impeller at a high velocity and accumulates in the volute. The volute is a chamber which spirals around the edge of the impeller. The volute chamber starts off small and increases in diameter as it reaches the exit. The increasing diameter causes the refrigerant to slow down, which will increase the pressure. As more refrigerant exits the impeller, this will be forced out through the discharge line and into the condenser. The capacity of the compressor is mainly regulated by the rotational speed of the impellers. The inlet guide vanes located at the suction inlet also provide capacity control, but usually only in periods of low cooling demand. They can vary their angle between fully open and fully closed. and a small internal stepper motor will move these. These triangular-shaped vanes will guide the flow of refrigerant gas, swirling it into the eye of the impeller at the most efficient angle, and also in the same rotational direction as the impeller. This makes it easier for the impeller during the low cooling loads when the refrigerant flow rate is decreased. The two impellers are mounted to the shaft, which runs the length of the compressor. This passes through 3 bearings. 2 will provide radial support, and a rear bearing provides axial support. These work together to hold the shaft in position. These bearings use electromagnets to levitate the shaft and suspend it freely. Sensors on the front 2 bearings will monitor the position of the shaft and feed this information back to the controller. The controller will make adjustments to the strength of multiple small electromagnets which surround the shaft. This will alter the position of the shaft and keep it perfectly aligned. When the unit is off, the rotor delevitates and rests on some mechanical bearings. The motor consists of permanent magnets in the rotor and a number of separated coils of copper wire in the stator. Each coil is connected to a different phase from the inverter. The bearing motor compressor controller module sends signals to control the on-off time of the IGBTs, allowing the inverter to vary the output frequency and voltage to the coils. When the current is passed through the coils, they generate electromagnetic fields which interact with the permanent magnets inside the rotor. This forces the rotor to rotate, and by varying the output frequency from the inverter, we can change the rotational speed of the impellers, which varies the capacity of the chiller. In the event of a power failure to the chiller, the permanent magnets within the rotor induce a current in the stator coils, effectively turning this into an electrical generator. This is then used to charge the capacitors for a short amount of time, but long enough to safely shut down the chiller and prevent damage. Check out one of the videos on screen now to continue learning about refrigeration engineering, as this is the end of the video. Don't forget you can follow us on Facebook, Twitter, LinkedIn and Instagram, and of course theengineeringmindset.com.